Good evening and welcome to all in lecture 2 of live lecture series of subject signal system KEC 403, and the topic is signal transform and their comparison, and I am Dr. Amit Garg, associate professor in EC department of AKGEC. So basically in this particular lecture I have tried to cover all the transforms like continuous time Fourier transform, discrete time Fourier transform, DFT, Laplace transform and jet transform, and basically their comparison. So the motivation behind making this particular lecture is that students are having various queries regarding what is DTFT, what is DFT, what is basically the difference between these transforms. Okay, so so let us start. So first of all, I would like to start with the signal decomposition. So before going through the transforms, first of all we should know what do you mean by signal decomposition. So basically the goal of the signal decomposition to extract and separate the signal components, because when we are having the signals wherein more than one frequency components are there, like your composite signals or non-stationary signals, so we require the frequency content of the signal, means what frequencies are actually present in the signal. So basically for proper analysis and processing of those signals, we require that we should decompose the signals in its frequency components. Like example, spoken words in speech signal, like if somebody is speaking something, and you can say if there is some noise element comes within that speech and we want to remove that noise component from the speech, then we have to take that speech signal and first of all we have to decompose that signal, and only then we can remove that noise part by using any filter. Okay, so signal decomposition techniques, if we will see, it includes basically it includes the Fourier series representation. So this is the representation. Basically in this particular representation, this is one of the representation in signal decomposition. So in this basically we will represent the signal in terms of linear combination of orthogonal functions. We will represent our signal in terms of linear combination of orthogonal functions. So based on orthogonal functions, if the orthogonal functions are trigonometric functions, we can call it a trigonometric Fourier series, and if orthogonal functions are exponential functions, then we will call it as exponential Fourier series. So basically this is basically a tool by which we can convert a signal from time domain to frequency domain, and also if we will take we can also synthesize again the signal from the frequency components. But the limitation with this Fourier series representation is that we can analyze only the periodic signals, means whenever we have to analyze the periodic signals or we want to decompose the signal which is of periodic type, we will use Fourier series representation generally. Means for aperiodic signals we cannot use Fourier series representation. So for some of the signals which are periodic we can obtain this Fourier series representation. Means in each and every case we cannot apply this Fourier series, that I will not include. Means the signals that follow this condition of Dirichlet condition, only those signals can be used to obtain the Fourier representation. Next come to Fourier transform representation. So Fourier transform is again a mathematical tool which changes a time domain signal into a frequency domain signal and vice versa. Means we can move from time domain to frequency domain, and also from, I will take the inverse Fourier transform, then we will again get back to the time domain, and basically we will use this Fourier transform representation for the analysis of aperiodic signals, and also we can use Fourier transform for the representation of periodic signals. Generally we will take those periodic signals only for which Fourier series representation is not possible in case of Fourier transform. Means Fourier transform can be taken for both aperiodic and periodic signals, but generally we will use it for aperiodic signals, and only those periodic signals for which Fourier series representation is not possible. Okay. Now one of the important question that came in our mind when we will go through this Fourier transform, that why frequency domain representation? Why we have to get the information in frequency domain when we are having the information in the time domain? So basically what happened when we will see a signal in time domain, then it may possible that we cannot analyze the signal completely in time domain. In some cases you can say information is not available in time domain, or you can say that in some cases it may also be possible that information is there but it is not visible. So what we can do, we can use the Fourier transform to convert the signal from time domain to frequency domain, and the properties like that we can easily view in frequency domain are like several characteristics of the signals that are either not visible or not easy to see in the time domain. Like you can say example, cyclic behavior. If we want to see the cyclic behavior of a signal, that it can be better seen in case of basically Fourier in case of frequency domain rather than in time domain. So that's why we require frequency domain representation. And as I have already told you that our aim is to do the signal processing later on. So what we want that our signal should be decomposed properly, or you can say it is based, the quality of the processing is based on the decomposition of the signal. So you can say if we can better decompose the signal, we will get the better processing of that signal. And for better decomposition of signal, we require information in frequency domain. Then types of transforms. So these are the transforms that I have already discussed that I will cover in this particular lecture are continuous time Fourier transform, discrete time Fourier transform, discrete Fourier transform, Laplace transform and jet transform. So basically these are 5 transforms which are basically in the curriculum, or you can say in this particular subject. So we will see one by one, and also I have made some comparison among these transforms. So if you will see CTFT, and CTFT is basically continuous time Fourier transform. So in case of CTFT, your xt or is a signal which is continuous. Okay, so your signal must be continuous and basically in this case aperiodic. Generally for aperiodic signals we are doing the Fourier transform, as I have already told. So for continuous time signal which is aperiodic, we generally use continuous time Fourier transform. In case of discrete time Fourier transform, our signal is discrete. Okay, so you can say signal is basically discrete and aperiodic. Okay, and another transforms I will cover as it comes in the slides. Okay, so all these transforms are used for the analysis of aperiodic signals or for periodic signals for which Fourier series representation is not possible, that I have already mentioned over here. Then let us start with the continuous time Fourier transform. So it is abbreviated at CTFT. So basically CTFT specifies the spectral content of a signal, thus providing a frequency domain representation of the signal. So an aperiodic signal can be represented as linear combination of complex exponential which are infinitesimally close in frequency. So the representation takes the form of an integral rather than a sum. Means you can say, if you will take the example of Fourier series representation. So what happened in case of Fourier series representation, because the signal is periodic, so there will be some definite period in that, but let us suppose we are taking a case of aperiodic signal. So in case of aperiodic signal, the period value is infinity. So when period is infinity, then you can say frequency components are almost, you can say at a distance of 0. So you can say you can observe the frequency as a continuous function rather than a discrete one. So this you can see over here. As the period becomes infinite, the frequency components form a continuum and the Fourier series becomes an integral. So you can say when we are applying that Fourier series for aperiodic signal, we are getting the concept of this continuous time Fourier transform. Okay, so now the expression that you can see for Fourier transform is basically x j omega, or you can also write it x omega. Some books use this x omega. So x j omega will be equal to minus infinity to infinity xt into e to the power minus j omega t, where your xt is basically your continuous signal. Okay, so what happened, if you will see from this expression, that what type of output you are expected, or what is basically the Fourier transform in this case, or continuous time Fourier transform. So if you will see, so you will find that continuous, if you will see x j omega, then you will find that x j omega will be somewhat this type of signal, which is basically you can say extended from minus infinity to infinity. Means you can say, if you will plot this x j omega, you will get that it is extended from minus infinity to infinity in frequency, and you can say, or you can see, this is basically an aperiodic signal. There is no periodicity in it. There is no periodicity in it. So this is continuous and aperiodic. So you can say, when you will take the Fourier transform of a continuous time signal, you are getting the output which is continuous and aperiodic. So this aperiodicity, you can say, due to this aperiodicity, what happened, this time information when converted into frequency information will go over here, means it will spread it from minus infinity to infinity. Okay, so that's why when we will take the inverse Fourier transform of this signal, what we have to take? We have to take this entire interval of frequency, so that you can see in the inverse transform, inverse Fourier transform. So xt will become 1 upon 2 pi minus infinity to infinity x j omega into e to the power j omega t d omega. So you can see here the limit is minus infinity to infinity, because for recovering the xt or time domain signal, we have to take this entire interval because it is aperiodic. Okay, so this is basically your inverse Fourier transform. So now it is basically represented like this, xt is the signal, and we are representing it like xt x j omega. So you can say this Fourier, this you can say signal, this is basically Fourier transform pair. So you can say a combination of xt and x j omega is nothing but the Fourier transform pair. Means, but one limitation of the Fourier transform is that when we are in time domain and we are taking the transform of the signal, then what happened? We are getting the information in frequency domain, but at the same time we lost the time information. And when we want to get the time information, basically, then what happened? We will take inverse Fourier transform, and in that case frequency information will be lost. So this is basically an issue, because when we are having a stationary type of signal, then this is not an issue, because generally we know that at what time which frequency is occurring. But when we are having a non-stationary type of signal, you can say this type of signal, then for better decomposition of this signal, we want the frequency and time information simultaneously, which is actually not possible with the Fourier transform. So this is basically the limitation with the Fourier transform, and this limitation will be overcome by the various transforms that basically we will not study in our curriculum. Okay, so x j omega or x omega basically is the spectrum of the xt, and it is a continuous function defined for all values of omega, that I have already explained. So now it is represented by x omega will be like this expression, x omega will be Fourier transform of xt, or we can write by this way. Okay, so what happened, this x omega or x j omega, we can write it in general, it is basically a complex function of frequency variable omega. So when it is a complex function, then for analyze it, we have to take the magnitude and basically the phase of this x omega. Okay, so we can write, if it is basically a complex quantity or complex function, we can write it xr j omega plus jxi omega, where xr omega is the real part and xi omega is basically the imaginary part. Okay, so when we will take the magnitude, how we will take the magnitude? When we will take the magnitude, so x omega will be mod of x omega will be mod of under root of xr square omega plus xi square omega. Basically this is the magnitude, and you know, for complex quantity what is the phase? Tan inverse xi omega upon xr omega. Okay, so this is basically about your continuous time Fourier transform. Now come to discrete time Fourier transform. So as I have already told you that like CTFT is applicable for continuous time signal, DTFT is applicable for discrete time aperiodic signals, discrete time aperiodic signals. And again the discrete time Fourier transform of a discrete time sequence is represented by the complex exponential sequence e to the power minus j omega n, where omega is the real frequency variable. So again this transform, like the other transform, all are frequency transforms, so they are converting time information into frequency information. Another important thing is that again when we will see the formula, again when we will see the expression for DTFT, we will find that This is generally represented by x, capital X e to the power j omega. This is the representation of DTFT. And it is not hard and fast that always we have to use this particular x e to the power j omega expression. We can also write it like x j omega or x omega, like in case of CTFT. So how we will differentiate between DTFT and CTFT? By two things. So, one is this xn, rather than xt we are using xn, and here rather than integration we are using summation sign. Okay, so this is the analysis equation. So you can see, when you will take the summation, here xn is discrete, but when you will take the summation from n equals to minus infinity to infinity with the complex exponential, and when you will obtain this x e to the power j omega, then important thing is that how x e to the power j omega we will get. We will get x e to the power j omega so you can say this is basically, again if you will see, if you will compare it with CTFT, you will find that it is basically continuous and periodic. So this is basically the difference between CTFT and DTFT. In case of CTFT, our spectrum is extending from minus infinity to infinity, and there is no periodicity between the spectrum. But here you can see, again if you will see the spectrum, it is extended from minus infinity to infinity in frequency, but you will find that this is periodic. Means the same information, when we are taking the discrete time Fourier transform of a sequence, the Fourier transform information, whatever information we are getting over here is the same information we are getting here and here. Okay, so what we can do basically, when we will take the inverse Fourier transform, then rather than taking this whole minus infinity to infinity period, we can take only some part of it, and this part basically if you will see DTFT, it is periodic with period minus pi to pi, or you can say 0 to 2 pi. So like minus pi to pi representation we are familiar, this is basically given in our books. So all the graphs that you will see is as per minus pi to pi representation, but 0 to 2 pi representation is generally used in simulation softwares like in MATLAB. In case of MATLAB, whenever you will see some graph or waveform in frequency, you will find that you are getting the information between 0 to 2 pi. Okay, so now we know that all the information of this signal will come in this minus pi to pi interval. That is why when we are taking the inverse discrete time Fourier transform, then what we are doing, we are taking the limit from minus pi to pi, because in minus pi to pi, because the information content is repeated here. Okay, so we will take only one cycle, and this cycle is from, you can say, minus pi to pi. So that is why, and this is continuous. So because this is continuous, so that is why we are putting here integration sign and limit minus pi to pi, and x e to the power j omega, e to the power j omega d omega, and xn will become 1 upon 2 pi. Okay, so this is basically the discrete time Fourier transform or inverse discrete time Fourier transform. Okay, so basically what is the difference between CTFT and DTFT? I think you people understood this thing. The difference lies that there is no periodicity in case of your CTFT. There is no, you can see here, there is no, it is aperiodic, but your DTFT is basically the periodic one. Okay, so the benefit of this periodicity is that we have to integrate from minus pi to pi only. Okay, then third one, you can see the periodicity of DTFT from here, like we can see here, we are taking this, just as I have already told you, that it is periodic with period 2 pi. So this we can see also mathematically. Okay, so this is our DTFT definition. Okay, so what we are doing basically, let us take an integer k, and we are writing it x e to the power, we are calculating the Fourier transform, rather than for j omega we are calculating it for e to the power j omega plus 2 pi k. Okay, so you can see here in place of omega you will get omega plus 2 pi k, then you will expand it, so you will get this e to the power minus j 2 pi n k. Now because in case of DTFT, n and k, whatever you are taking basically are integers. So when these values are integers, then e to the power minus j 2 pi will always become 1. So when it will become 1, then you can vanish this term, so you will get this term. So you can say x e to the power j omega plus 2 pi k is x e to the power j omega. So it means you can say this signal is basically, you can say DTFT is periodic, Fourier transform or DTFT is periodic with period 2 pi, or you can say multiple of 2 pi. If you are putting the value of k from 1, 2, 3, 4, so you can say it is periodic with period 2 pi. Okay. So this I have already explained previously. So this is basically about periodicity of DTFT. Now comes to the another transform basically, which is your discrete Fourier transform. So what is the issue with the DTFT? So in case of DTFT, we have seen that we are taking a signal xn, which is basically your discrete signal. But what happened when we are taking DTFT? What we are getting? We are getting x e to the power j omega, which is a function of omega and continuous. Okay. So what happened? If x e to the power j omega is basically continuous, then what happened? It will consist of infinite frequency points. Okay. So let us suppose we have to analyze this signal using some simulation software or through a digital computer. So you know, in case of digital computer, infinite values cannot be stored. So what we can do? In that case, what we have to do? You can see here xn is discrete, so there is no issue, but here it is continuous. So when it is continuous, so we cannot deal the continuous values through the digital computers. So what we have to do? If we can discretize this signal also, so what we will do? We will discrete it. So if we can discrete x e to the power j omega, then our signal is discrete and also Fourier transform will be discrete. So discrete Fourier transform is actually discrete time discrete Fourier transform. So we will call it, simply we will call it discrete Fourier transform. So in case of discrete Fourier transform, what is this discrete Fourier transform? If you will see the DTFT, okay, so you have seen the DTFT, let us say this is one period of DTFT, okay, which is extending from minus pi to pi, or simply you can say 0 to 2 pi. So you can see between 0 to 2 pi or minus pi to pi, infinite values of frequencies are present. So again this is the same case I have told you. So what we can do? If we can discretize this 0 to 2 pi interval by doing sampling in frequency domain like this. So what happened? Now our information will be discretized. Rather than taking infinite values of omega or frequency between minus pi to pi or 0 to 2 pi, we are only taking the magnitude value. This is basically omega versus magnitude. Okay, so you are taking only some magnitude values at discrete frequency points. Okay, so what that discrete quantity, let's say that is k. So we are representing it by k. So now what we are doing? Basically what we are doing, we are putting it values like 0, 1, 2, 3 like this. So what we will do? Basically now we are discretizing this omega, or we are doing sampling in basically in frequency domain. Okay, so we are doing sampling in frequency domain. So what is the benefit? The benefit is that rather than getting infinite points, we are getting some finite points only. Okay, so you are representing it like, now how we will divide it and in how many points we will divide it? Let us suppose we are dividing this 2 pi interval in n points. Okay, n points means we are getting the value of magnitude only at n number of points. Okay, so what will be the separation between 2 points? Then it will become 2 pi by n is the separation between 2 points. Okay, and k is basically the index. So what we are doing basically, by this k we are reading these points, okay. So omega will be equal to 2 pi by n times k, where k is varying from 0 to n minus 1. Okay, so what happened? So we will get these points. Okay, we will get these points when we will use this expression. Okay. So another important thing is that in case of DFT, the sequence that we are using is of finite duration. We cannot take the DFT for infinite duration signal. We have to take finite duration signal, and the DFT that we will get is also discrete, means for n points. You can see the drawback in DTFT is that the frequency domain representation of a discrete time signal obtained using DTFT will be a continuous function of omega, and so it cannot be processed by digital system, that I have already explained. DFT has been developed to convert a continuous function of omega to a discrete function of omega, so that frequency analysis of discrete time signals can be performed on a digital system. So for the analysis point of view with the digital systems, we have to also discretize this. So how we will get the equation? Now, as I have already told you, if you will see the expression, this is basically the expression of DFT. Okay, so you can say it is represented by xk, and you can see here summation n equals to 0 to n minus 1 xn e to the power minus j 2 pi nk by n. So how it comes? If you will see the expression for DTFT, you will find that expression is summation n equals to minus infinity to infinity xn into e to the power minus j omega n. This is for DTFT, which we have seen previously. Okay. As I have told you, when we will take DFT, then our sequence must be of finite duration. So what we are doing, let us suppose there are n points or length of the sequence is n. So we are putting the limit 0 to n minus 1. Okay, xn is there, and what we did in case of DFT, we have discretized this frequency. Okay, so how we have discretized, I have already explained. Yani omega will become 2 pi by n times k, and now you are varying the value of so you can represent omega will be equal to 2 pi k by n. So you will write it e to the power minus j 2 pi n k by n. So this is how comes the definition of DFT. Okay, where k value is varying from 0 to n minus 1. So now how you can compute this discrete Fourier transform? This discrete Fourier transform can be computed like you will take the value of k, let us say for each and every value of k, you will calculate this whole summation every time. Means x0, for x0 you have to put value n from 0 to n minus 1 every time. So there is one thing over there, like in this expression I have chosen n equals to 0 to n minus 1. We can also write it like L minus 1. So why it is so? Because n is the number of points of DFT, and here what we are doing, basically we are reading the sequence. So basically this n represents the length of the sequence. So let us say rather than n I am writing it L. So L is the length of sequence. Okay. So one condition for DFT is that you have to always take n greater than equal to L. N greater than equal to L. It means what? You will always take the number of points of DFT larger than the length of the sequence, which is represented by L basically. But for analytical easiness, we are choosing n equals to L. Means we have to take, let us suppose we are having a sequence which is length 4, then we have to take 4 point DFT of that sequence. We have to take 4 point DFT of that sequence. We can get for more points of DFT for length sequence. Means if length of the sequence is 4, then at least we have to take 4 points DFT, or we can take more number of DFT. Means we can take 8 point DFT, we can take 128 or 256 point DFT, but for analytical easiness, this expression we are writing L equals to n. Okay. Similarly, corresponding IDFT, if you will see, the expression is this: we have to divide by 1 by n, summation n k equals to 0 to n minus 1 x k e to the power j 2 pi n k by n, where small n is varying from 0 to n minus 1. So difference is that here you have given xk value and here you have given xn value, so that is why you are varying k, and here you have to vary small n. Okay. So this is about your DFT. Now from this chart you can easily see what is CTFT, DTFT and DFT. So in case of CTFT, you can see the signal is continuous and aperiodic, which we have already taken, and the spectrum is like continuous and aperiodic. Okay, you have seen. In case of DTFT, your sequence is of infinite length, aperiodic, discrete sequence, and you can see here the spectrum is periodic. Again the same thing appears. Of basically DFT, what happened? Our sequence is basically discrete and periodic, and also when we will take its DFT, it is discrete and periodic. Okay. So that is why when it is discrete and periodic, then here it is also here discrete and periodic. So we can use DFT by default for the digital computer. So whenever we have to take the Fourier transform, then we will prefer DFT, and in case of DFT, if you will compute it through MATLAB, then for performing DFT we are having a fast method that is called fast Fourier transform. So we will use the command FFT, you know. Okay. So these are about CTFT, DTFT and Laplace and DTFT and DFT. Now come to the another transform, important transform, Laplace transform. So how this concept of Laplace transform came? One of the problem associated with the CTFT is that many of the input signals do not have Fourier transform. Like Fourier transform, you know, the Fourier transform exists when it exists when the function is absolutely integrable basically. So if our signal is not absolutely integrable, so that we cannot, or you can say signal is not converging, then in that case we will not be able to take the Fourier transform. Examples are e to the power at ut, e to the power minus at when t is minus infinity to infinity, or tut. These are the signals that are not absolutely integrable signals. So we cannot take the continuous time Fourier transform for these signals. So basically you can say Laplace transform is nothing but the extension of CTFT, extension of CTFT. So what we have extended over here? We have resolved this issue of absolute integrability of some signals. How? If you will see the Fourier transform, in that case, or in case of CTFT, we are using e to the power j omega t, means our analysis is restricted over this j omega axis only. Okay, there is no sigma is not there. Okay, so our whole analysis is restricted only over the j omega axis. So what happened? We are checking the signals for absolute integrability at j omega axis, but in case of Laplace transform, we have changed the definition. Rather than taking j omega, we are using this transform uses S plane, okay, where S equals to sigma plus j omega, where sigma is basically real part and j omega is your imaginary part. Okay. So what happened? Now this is sigma, which is the real part, of S. Okay. So what happened? In case of CTFT, this sigma is 0 in CTFT, okay, because you are working on j omega axis. So when sigma equals to 0, it will become CTFT. So now if we, rather than 0, we are taking some value of sigma, let us say sigma equals to 2. So it means sigma equals to 2 means we are having some plane over here which is parallel to this j omega axis. Now, but now this time real part will be there, and due to that real part, maybe the signal which was not converging over here maybe converge over just a minute. issue है. इधर आ गई हैं. Okay, sorry for the interruption. Okay, so now rather than taking this point, we are taking it here. Okay, we are taking it here. So maybe it may be possible that the signal which was not converging over here may be converging over here. Okay. So you can say the Laplace transform is basically used to transform a time signal to complex frequency domain. In case of continuous time Fourier transform, we are converting time signal into frequency domain only, but here we are converting it into complex frequency domain where both sigma and j omega will be there, means both real and imaginary part will be there. So this is about Laplace transform. The Laplace transform possesses a distinct set of properties for analyzing signals and LTI systems. So you can, another thing is that here it is written Laplace transform properties are parallel to those of CTFT. So this is the simple concept that if you know the Laplace transform for a particular signal, you will check that for that signal if Fourier transform exists, then you will simply write S equals to j omega in the expression of Laplace transform, then you will get the CTFT. Okay, but for that we have to check the convergence, we have to check the region of convergence. So what is basically the region of convergence, that we are coming soon. So first of all we will see this what is the Laplace transform. So you can say Laplace transform finds in two ways, one is bilateral Laplace transform, another one is unilateral Laplace transform. So previously you have seen the CTFT equation, that is xt into e to the power minus j omega t, but this time we are putting it like in place of j omega we are using e to the power minus st. Why we are calling it bilateral? Because the limit is from minus infinity to infinity, means causal and anti-causal both type of means we are taking, and here limit is from 0 to infinity. Unilateral Laplace transform means we are only taking the right half of the S plane, and here we will conclude the here we will take the complete S plane. Okay, and inverse Laplace transform is this inverse Laplace transform is basically evaluated using this and inverse Laplace transform is basically represented by this expression. This is the contour integration expression, and it is somewhat difficult to basically calculate. So but generally we don't use this formula, other than contour integration method we don't use this method. We are having another methods for calculating the inverse Laplace transform, that are basically your contour integration method or power series expansion method or basically your partial fraction expansion method. Okay. Now come to the region of convergence. So you know the Laplace transform signal is given as xs equals to xt into e to the power minus st dt, where the values of sigma or real part of s for which the integral converges is called the region of convergence. So region of convergence, basically we will check that in case of CTFT the sigma value will become 0, but here some value of sigma will be there. So we have to check for which values or which range of sigma values this signal converges, or you can say absolutely integrable. Okay. So ROC consists of those values of sigma for which CTFT of xt into e to the power minus sigma t converges. You can say right now if you will write s in place of this, if you will write like minus infinity to infinity xt, and if you will put s equals to sigma plus j omega here, so you are having xt into e to the power minus sigma t into e to the power minus j omega t dt. So if you will see right now what we are doing, basically we are taking the Fourier transform of xt into e to the power minus sigma t rather than xt. So what this e to the power minus sigma t terms doing, basically this term is doing, this term is basically used to converge the signal which was not previously converged in case of simple CTFT. So by limiting the value of sigma in certain range, we can ensure that value of xt into e to the power sigma minus sigma t is absolute integrable, although xt is not itself absolutely integrable. Okay. So if we here it is written that ROC provides information about whether xt is Fourier transformable or not. The condition for the same is that ROC of xs must include j omega axis as in case of CTFT sigma equals to 0. So this is just I am telling you, let us suppose we are having a signal for which we are having region of convergence like this. Okay, I have just taken example, and this is corresponding to j omega axis. So if we will check if the ROC of Laplace transform covers the j omega axis, in that case this signal is Fourier transformable also, and if this signal is Fourier transformable also, then what we can do, we will simply write S equals to j omega in the expression of Hs, and we will get H, basically we will get the Fourier transform. Okay. Okay, so it is written over there. So you can see here, so based on the observations, this is your imaginary axis, and these are two poles, one is at B and one is at minus B. So region of convergence is basically not included these poles, but depending upon these poles, let us suppose this pole is B. So how we are getting this pole, let us suppose 1 upon S minus B will be there, which is the term contributing this pole, and 1 upon S plus B is the pole which is contributing basically this pole. Okay, so if these poles are there, then when we will check the ROC, so if this pole B corresponds to 1 upon S minus B, so it means the ROC for this is basically causal one. Okay, so if it is causal one, then it is basically the right sided. Okay, and if it is minus B, and you can say it is corresponding to anti-causal signal, then the ROC will be left sided, or the simple rule is that ROC will always be parallel to j omega axis. If the signal is causal, then the ROC is outside the rightmost pole, and if the signal is anti-causal, then in that case the ROC is left side of the leftmost pole. And also when you are having a non-causal signal, in that case your ROC will be a parallel strip, the parallel strip that will cover the parallel strip means one pole is corresponding to anti-causal signal, another one is for causal one. Okay. So for causal signal simply ROC is right sided, for non-causal for anti-causal signal ROC is left sided, and for non-causal signal basically ROC is a strip basically, okay, parallel to j omega axis. Okay. Now come to the jet transform. Basically jet transform is the discrete time counterpart of the Laplace transform. Like you can say you have seen CTFT, the extension of CTFT is Laplace transform. You have seen DTFT, the extension of DTFT is jet transform. Okay. So what is the issue with the DTFT? Again the issue with the DTFT is that again we are working on the if you will see jet plane. First of all we should understand what is jet plane. Jet plane is basically like this, it is just like a circle here which is having radius r, and angle which is it is making from is omega. So in jet plane we are representing the signal by z equals to r e to the power j omega. So what happened in case of DTFT, we have fixed this value r equals to 1. So r equals to 1 for DTFT. So we are restricted for our analysis over this unit circle only. And what happened, like CTFT we have seen some signals for which for CTFT is not possible. Also there are some signals for which DTFT is not possible due to the convergence issue. Or you can say those signals are not basically absolute summable here, not integrable, because we are working in discrete domain. So absolutely summable basically. Okay. So what happened, rather than restricted our analysis over r equals to 1, so what happened, we have restricted our analysis for r equals to 1 in case of DTFT. So jet transform gives us liberty to change this value r, in such a manner so that the signal will become absolute summable, so that we can take its transform. So what we can do, we can do the change, we can take the value r less than 1, we can take the value r greater than 1. Okay. So you can say you can restrict your analysis not only on this circle, unit circle, but you are restricting your analysis over this point or over this circle. Okay. So in that case you can see you will choose the value of r in such a manner so that your signal will become absolutely summable. Okay. So you can see, now we will read this. So jet transform enables us to analyze certain discrete time signals that do not have a discrete time Fourier transform, that I have already explained. The jet transform plays the same role in the analysis of discrete time signals and LTI systems as the Laplace transform does in the analysis of continuous time signals and LTI systems. Again, it will come into two variants or two varieties: bilateral or two-sided jet transform, or unilateral or one-sided jet transform. Bilateral transform offers insight into the nature of the system characteristics such as stability, causality and frequency response, and the unilateral jet transform is a convenient tool for solving differential equation with initial conditions. Means generally bilateral, by default the transform is bilateral jet transform, but when we will analyze the solution of difference equation, in that case what we have to do basically, in that case we have to take this unilateral Laplace transform and unilateral jet transform, and in unilateral jet transform limit will be start from 0 to infinity. So this is the expression for bilateral jet transform and this is for unilateral jet transform. You can see here is the limit from minus infinity to infinity and here is from 0 to infinity. Okay. So this I have already explained. In z equals to r e to the power j omega, where r as the magnitude of z and e to the power and omega is basically the angle of z. Okay, so you can see here now in place of z we are writing r e to the power j omega, so you can say xn into r e to the power j omega to the power minus n. So what is this basically? If you will see, this is the expression of DTFT. So you can see this time we are taking the DTFT of xn into r to the power minus n rather than simply xn. So what happened? Due to this r to the power minus n factor, the signal which was not actually absolutely summable previously will now become absolute summable due to the multiplication of this r to the power minus n factor. So this basically this r to the power minus n may be decaying or growing with increasing n depending on whether r is greater than or less than unity. Okay. So you can say jet transform is nothing but the Fourier transform or DTFT of xn into r to the power minus n. Okay. Now region of convergence, the range of values of mod z equals to r for which the jet transform converges is termed as the region of convergence, that I have already explained. That is, the ROC consists of those values of r for which the DTFT of the xn into r to the power minus n converges. Note that the jet transform exists for some signals that do not have a DTFT. Why? Because rather than taking xn this time we are taking xn into r to the power minus n. So this I have already explained, I think. Important thing is that if you are having jet transform, let's say you are having xz value, and you want to obtain the DTFT value from this jet transform. So what you will do, you will simply put z equals to e to the power j omega in the expression of xz, so that you will obtain basically the x e to the power j omega. But this is only possible, and this thing you can only do when you will find that the signal is Fourier transformable. And what is the condition for Fourier transformable? If you will see, let us suppose this is basically unit circle radius, okay, and your ROC is somewhat maybe like this. So you can see here this r equals to 1 circle is overlapped by the ROC. So if this condition exists, it means Fourier transform is also possible for this particular jet transform. So we will simply write z equals to e to the power j omega here. Okay. So this is about your DTFT, or this is about your jet transform. Now this is the summary or the comparison among the jet transform. So this is very important chart that I have made. So here I have written type of signal and spectrum, and here all the 5 transforms: CTFT, DTFT, DFT, Laplace transform and jet transform. So you know, if continuous time signal as an input is there, then only CTFT is possible and Laplace transform is possible. DTFT, DFT and jet transform is applicable only for discrete time signal. This you can see here. Okay. Means for CTFT, for continuous time signal you can take either CTFT or Laplace transform, or for discrete time signal you can take DTFT. For discrete time signal you can take DTFT, DFT or jet transform. Then periodic signal, as I have already told you that periodic signal, you can also do the Fourier, you can also do the transform for periodic signals. Okay, so that's why I have written yes, means for all the transform you can for periodic signal you can do all these transforms, or you can apply all these transforms. For a periodic signal, yes, CTFT is there, DTFT is there, Laplace is there, jet transform is there, but DTFT, for DTFT your signal should be periodic, that's why here I am written no. And finite duration signal, you know, in case of CTFT signal should be infinite. Okay, if your signal is finite, then you can only do the CTFT when you will extend that signal up to infinite extent, that's why I have written no. Otherwise you can say yes also when you are going to extend your finite duration signal. And in case of finite duration signal, yes, you can do DFT, DTFT, you can do DFT, you can not do Laplace transform, and you can do jet transform also. And for infinite duration signal, if the signal is of infinite duration, yes, you can do CTFT, you can do DTFT, but DTFT is only applicable for finite duration signal, and Laplace transform yes, and jet transform yes. Now talking about the frequency spectrum. Okay, so continuous frequency spectrum you have seen in case of CTFT yes, in case of DTFT yes, both are continuous, in case of Laplace transform yes, in case of jet transform yes. Okay, so here the spectrum comes in the condition when we are assuming that from this Laplace transform I am going to put s equals to j omega or z equals to e to the power j omega over here, otherwise spectrum comes in this case only. Okay, so discrete frequency spectrum, no, CTFT gives us continuous spectrum, this DTFT also gives us continuous spectrum, but DFT spectrum is basically your discrete one, and Laplace transform also not give this, and jet transform also not give this. Then periodic frequency spectrum, so you know the frequency spectrum is periodic in case of DTFT and DTFT both. Okay, so you can say it is for applicable for jet transform also. Aperiodic frequency spectrum, in case of CTFT aperiodic frequency spectrum, that's why I have written yes over here, and others are no, because you are getting periodic frequency spectrum. Finite duration spectrum, in CTFT no, you are having infinite duration spectrum, and in case of DTFT we are also getting infinite duration spectrum. Here for DFT yes, we are getting finite duration spectrum, and for Laplace transform no, and jet transform also no. And infinite duration spectrum in CTFT, in DTFT, and in Laplace transform and jet we are getting infinite duration spectrum, and for DFT it is no. Okay, so now so for now I am ending this lecture. So if anybody is having any doubts regarding the concept, then you can ask. So if there is any query, you can write it on the chat box, so I can answer it. So I am waiting for a while. So these are the simple concepts by which we can understand all these transforms. Okay. 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 So if there is no query, then I am ending this lecture. Thank you so much for your kind support. Thank you.